Right, so Ian is speaking here because he and I have been communicating by phone. He's doing very interesting work with teaching Haskell and needs sponsors for the work. So depending on how this goes, maybe somebody at Edinburgh will end up sponsoring this work. So I'm really looking forward to this talk. The idea of combining Cuisenaire rods are one of my favorite things. I guess you're going to show them off in a minute. I remember them very well from when I was I think I was in kindergarten, maybe first grade, I think kindergarten. So the idea of combining those with Haskell sounds really appealing. I'm really looking forward to this talk. So Ian's an honorary research fellow at the School of Education at the University of Roehampton. He's director of the Social Mathematics CIC, which is a social enterprise. I'm not sure, what is a CIC?
It's a community interest company.
Ah, community interest company, okay, which is a social enterprise. He received his MA in mathematics and his PhD in computer science from the University of Cambridge. I've heard of that university. And his master's in symbolic systems from Stanford University, which I've not only heard of, but attended as an undergraduate. And he served as a trustee of the UK Association of Teachers of Mathematics from 2015 to 2020. Ian's written or edited 5 books on the social, economic, and educational implications of computer technology. And one of these books is The Primary Mathematics, Lessons from the Gategno School, which I think will be the basis for what he's talking about today. So I'm really looking forward to hearing what you have to say, Ian.
Thank you, Philip. Thank you, Philip, for inviting me and
You have to thank Ohad. He invited me.
and Ohad for setting up the very complex technological environment we have here to do simultaneous face-to-face and remote. If the signal goes, I'm sorry, there isn't a backup, so we're living dangerously here. So my talk's got 3 parts. The first part is going to give you the history of the approach that Gategno developed to teaching algebra with the rods. The second part is going to give you, for the first time, I've spoken about this, the piloting of Haskell with year 2 children, which we've done for about 16 hours, 20 hours of teaching in classrooms. That builds on the Gategno mathematics. And the last part of the talk, which I was asked to put in by Philip, is somewhat tentative. It's how we might develop teacher training resources based on the assumption that teachers have a GCSE in maths, a GCSE C level in mathematics. That's the level we're pitching these exercises. And I've taken an exercise which we're beginning to develop for teachers. So we've worked since 2004, educating teachers and learners in over 25 schools, with more than 500 students following Gategno textbooks 1 and 2. Our studies at Stanford, with colleagues in the School of Education at Stanford, have run an experiment for the last 2 years, modeling the children's understanding both of algebra and fluency with arithmetic. We've reported in the open access realm our research results, which are subject to peer review and publication. And I'm not going to talk very much about that, although I'm very happy to do it in Q&A and at the dinner afterwards. Our proposal now is to add contributions in computer science, particularly in domain-specific languages, interface, and participatory design. We want to build a 3rd year of the program, having taught algebra in year 1 and 2. And the 3rd year will concentrate on teaching Haskell to young people who've had the preparation in years 1 and 2. Our central concern—
Years 1 and 2 means first grade and second grade?
Yes, you have to align the grades very loosely, because here we start teaching children a year earlier than America. So
when you say year 1,
I'm meaning the work is done in England with children who are 5 years old. Our central concern is how can we create an appropriate development environment for 7-year-olds, and how best can we design this environment with the teachers. We will address the key problem of in-service teacher professional development by putting early algebra together with Haskell programming.
That's really great. Can I actually just go back to one thing? You had this textbook that they talk about.
The textbook here, yeah.
Right. Who is he? How old is that book? What was that the book that introduced Cuisenaire?
Yeah, that is the book that introduced Cuisenaire. And Guiteneau was a pure mathematician who decided to work in education. He's best known in the UK for his work as a maths educator, but in France today, he's best known for his work on literacy, and in Japan for his work on language teaching. He was able to work across curricula like this because he had a model of learning which he could apply in different domains. We've adapted this model of learning to learning and teaching mathematics with Haskell. So that's Guiteneau. The rods, on the other hand, have a life of their own. They are found in almost every classroom, in a classroom in almost every school in the UK and in many schools around the world. And they have survived being taken out of the cupboard periodically because they're very helpful for children with learning difficulties. But the curriculum and the book that we just alluded to has been more or less forgotten. And the job we took on for the government was to reevaluate why it had been forgotten and to suggest ameliorative ways of getting value out of it. It's been argued that mathematicians who are familiar with Guiteneau's work have argued that it's important, his theory of learning is important to address continued patterns of failure in national government reforms of mathematics. And one of my colleagues, John Mason, has put it this way. He said, these projects fail because they focus on behavior. That is to say, they regard mathematics as something that's going to be transmitted to the child, like a waterfall, rather than treating teachers and pupils as having a relationship with each other and failing to attract the student to work with on the situation, on the mathematical situation that was being offered. So what Guiteneau said was, if you're going to change teaching to subordinate it to learning, then you have to teach algebra first before arithmetic. And you can see here in this slide, which I'll spend a second or two elaborating, this is work that was reported from 1964 of a student in grade 1 in Canada, age 6, after 4 months of work with the textbook and the rods. They were invited to freely write equivalent expressions evaluating to 10 and to 12. And so Louis Paul is saying here, 10 is a half of a half of a half of 80, which is equivalent to a third of 30, which is equivalent to 4 and 7 take away 1, which is equivalent to the square root of 100, which is equivalent to the cube root of 8, plus a half of 4 times a half of 8 times a half of 2, and so on and so forth. He's using all 4 operations, unit fractions as operators, and powers and surds effectively. Now, faced with this evidence, the reaction of the teaching profession has been either to say, these are exceptional children and exceptional teachers, we can't do that, or to say the mathematics that was taught in 1964 is the same as mathematics today. The teachers are the same as the teachers in that. Sorry, the children are the same and the maths is the same. The only thing that's different is the teacher. And the teachers have then opened themselves to learning more about this approach, and we found very effectively collaborating with us on reanimating the curriculum in classrooms. So the curriculum is defined in a set of textbooks, there are 8 of them, a book for teacher education called The Common Sense of Teaching Mathematics. In the back of this book is a curriculum graph which shows the logical dependencies between concepts in this curriculum. And the root nodes of this graph, which is a directed graph, so the arrows point between conceptual dependencies, they point from 5 root nodes, permutations and combinations of rods equivalent in length to a rod of a particular length. This is all the permutations and combinations. And then a restriction I call measure, which is just the all white train. A table I'm calling the Ferrer table for reasons I'll discuss in a minute, which has 1 train representing all the permutations of that combination. The complements table, which has got pairs of rods equivalent in length to a rod, and the divisor table, which you could define as trains of one color or trains with two colors with fewest cars for the colors that aren't represented in the one color trains. Now, combinatorics and conceptual mathematics are two distinct subdisciplines of mathematics which have come together in this program as recommended by Gitenio. But this isn't the only way the two subjects can come together. And so I've published a series of articles, which again, I haven't got time to go into now because this is not about conceptual mathematics, but they talk about automorphisms and external and internal diagrams illustrating these concepts with the rods. So they've become a very versatile mechanism for following Giudone's intuition here that there's valuable mathematical research to be done. We've consolidated our understanding in two books. One, Roslang and Piers Messam have written, which bring together Gitenio's theory of learning, and one that I put together of the teacher training materials we used in the first few years of the project with teachers very successfully. The key that unlocks mathematics to Gitenio is this graph he put together of the unfolding or the cycle of the unfolding of mathematical activity. People take action, which is driven by perceptions, which generates imagery, mental imagery. That mental imagery can come from using physical actions or virtual actions, imagery generated by the action. The imagery can then be articulated in language, which can be a formal or informal language, and it can be captured in symbols. And these come together in definitions, and the definitions communicate the mathematics. So if there's one thing that you take away from this talk, it's this model of the unfolding of mathematical activity. Each of these cycles of work involves its own particular objects, elements, and manipulations. Its own, in Gitenio's scheme of work, its own permitted diagrams, transformations of the diagrams, names, algebraic and arithmetic names that you can give to the diagrams. But the learning process is common. The curriculum graph shown here descends from those study of these prototypical patterns. So very early on, you study addition, subtraction, multiplication. And then on the right, on the left here, the graph begins to talk about concepts which are not in the school curriculum, equivalence, order, which put together with the traditional curriculum lead to an understanding of powers and number systems. What you're going to see in a minute is a film and some examples of children's work as they make their way through the curriculum graph for the first 2 years. Yes.
What's your definition of imagery?
I've defined it as a conceptual model. So it has some structure to it. And I'm relying on Gitenio's giving me prototypical imagery, or I call it an ideograph. So it's a well-formed diagram in some sense, but he's already codified a number of them. And here's one at the beginning. Each of these boxes, which are kind of loosely, you could identify with categories, represents one image. So there's the image that's provoked by sorting the rods. You open the box up, you put it, you mix it all around, you pull out the rods and sort them by color. You do the same thing again and sort them by length. And you observe that the two heaps, the two sets of heaps that you get are equivalent. That they have a notion of a common sorting process. And that's treating the box of rods as if each individual rod is a distinct element and sorting according to equivalence classes brought on by that relationship. The next thing that children are asked to do is to explore the difference between two rods when they're put side by side, and to give a name to that construction using the greater than and less than symbol. You might loosely say that's a category which has got some order relationship amongst the rods. They then move on to studying staircases or families with equivalent differences, which you could represent as a chain of greater thans or less thans. And finally, sorry, I'm going the wrong way around. It's that we fill this gap to get an equation of this form. A dark green and a red is equivalent in length to a tan. Then we take it away and we get the family of equivalent differences. So what I'm going to show you in a minute is some work the children have been doing, starting with a game where they take the rods behind, they take a subset of the rods behind their back, and they're asked to identify what the rods are by their touch.
So we've got the white, the red, oops, see, another rolling, and then the dark green. Pop them behind your back. Okay, right then, who can hold up without peeking, just by feeling the white rods? Who can hold it up? Okay, you got it? Good girl. Super. Brilliant. Right, put behind back again. Behind back again. Who can hold up the dark green?
Dark green's here.
Oh, did we not put that one behind the
Light
back?
green.
Light green then. Silly me. Good remembering that you knew that wasn't even in your hand. Okay, who can hold up the yellow? Who can hold up the yellow? Oh, good girl. How did you know that was the yellow?
Because it's the longest.
It's the longest in your part.
So as I say, they give the color, the rods are given color names, then they're given color code letter names. And there are in the literature several different coding systems. Catenia's, which we'll be seeing in a minute, just ambiguates the black, the brown, and the blue by using capital B for the blue, T for tan for the brown, and B for black. I've been using another coding system which is more akin to Haskell hints. The colorblind children are obviously at a disadvantage with it, but in practice, because the shapes are distinct, they can distinguish them by their lengths. And in practice, they're able to work effectively with the color codes. So by the end of the first term of the first year of schooling, the children are reading and writing equations in this form. Green is equivalent to a multiple of 3 whites, and at the same time, a white is equivalent to a third of a green. Dark green is equivalent to 3 reds, and a red is equivalent to a third of a dark green. So the concept of a unit fraction as an operator is introduced at exactly the same time as numbers are introduced as multiples. He also asked the children to write equations and then to classify them as to whether they're valid or not. So this equation says 3 whites plus a third of a blue is equivalent to dark green. And this one says a 1/7 of black and a 1/5 of orange is equivalent to a green. The teachers give the children the opportunity to sort these equations into true or false categories. And as you can see here, that exercise is done on the whiteboard or at the desk. They go on in the beginning of the second year, the beginning of the second term of the first year, to give number names to the rods. Obviously, if you measure with a white, this becomes a 6. And they start expressing equivalent expressions for numbers up to 30. Here, 24 is 5 plus 5 plus 5 plus 4, or it's 3 8s, or it's 3 times 2 times 4, and so on. This is all free writing and free creative work by the children.
Just for me to check, in a normal curriculum for 5-year-olds, I wouldn't expect they would have seen division. Would they have seen even multiplication?
No, no.
Right, so all of this is quite intense compared to what they normally.
Yes, what happened in 2014, the British government changed the national curriculum statutory requirements so that children should have all 4 operations and fractions as operators for small numbers in year 1. Prior to that, it was exactly what you said. That was the norm. And it was because they changed the statutory requirement that we were able to start working with children and schools again. Up to 2014, it was really hard to find people to pilot this stuff. After 2014, it was very much more fruitful for us and for the teachers. What subsequently has happened is that the government's rowed back in non-statutory guidance. So it's no longer required in England that children study all these operations at the same time.
You know what's required in Scotland?
I'm afraid I can't answer that question.
That's fine. Go on. This is really interesting.
Free writing leads you into creative programming. And the step here of writing their own equations, or in this example here, I'll just read some of these are function instances they're given, and they're asked to sort the function instances into the functional definitions. So this function is doubling, it's going 2 to 4, 11 to 22, 21 to 42, and so on. Those are in the column, it's been doubled. This is the halving column, this is the tripling column, this is the 4 times column. So they're being introduced to sorting expressions in the way that they were sorting the rods. At the outset, we started virtual manipulatives, working with virtual manipulatives in the classroom, and we found that children used them to check their work. They could take an equation that they'd written and work with the virtual rods to build the pattern that it described and check whether or not it was valid. And then in 2016, we deployed an interactive development environment on an iPad. The children had one each to work with, and we gave them this data structure to model the staircase. Now, as you know, there's a lot of rich structure sitting behind these deriving. One of them might be missing. Yeah, that's certainly possible. Okay, so can you tell me what is missing? The black is there. What after black? Tan is missing. Okay, fair enough. Is it there? Yeah, it's missing from this one as well. But the point I'm trying to make with this slide is that the children, once they were given the data structure, started writing expressions to see what the boundary conditions were in using it. So we gave them the successor operator, which was inherited, and we taught them about of, so that you could apply functions to the results of functions and compose them. And this child's asking what the successor of the successor of the predecessor of green is green. Of course, she could have put another of pred at the beginning, and then it would have crashed the system, because the boundary doesn't let you go any further back than white. However, there was enough value even in that little bit of programming that the children could start modeling their own computations with the kind of problems they were going to meet and did meet in the standard assessment tests at the end of year 2. So here's an example of a problem. There were 20 cars leaving the car park. They went left or right. 10 went to the left. How many went right? And the children are able to write down a representation of the problem, a model of the problem, and then write down their working as if they're mentally interpreting the named values. The barred arrow for invocation of the functional or evaluation of the named int is separate from the assignment use of equals here. And they could go on and take a kind of problem that another problem they get in the standard tests, where they're asked, what is if strawberry and orange, if strawberry is 24 and a strawberry and orange is 98, what is the orange? And fill in the gaps, fill in the empty squares. They write down they're working, the strawberry is equivalent to 24, and orange is, both are 98, the orange is the difference between them, so the orange evaluates the 14. All the learners managed to do the calculation. Some had difficulty with editing on the iPad because it's a bit finicky, touch sensitive. A third of the children used the barred arrow to report their work, and one confused the barred arrow with equals. So the second program, we introduced not a color as the unit and explored the execution of the program by visualizing it as the table of complements. So the first stage in this sum is here. Equation 2 then gives you that equivalent expression, that one, and then finally the unit ends the recursion. As I said, the children were keen to explore the boundaries of the calculation. So they took the set of relationships between the rods, which they'd studied with Quintanillo's textbook. There's a series of equations. Green is equivalent to 3 whites, pink is equivalent to 2 reds, a red is equivalent to 2 whites, and so on, and changed the initial value for W, and then interrogated the interpreter to see what the changed values for the other color codes were. And here I'm going to show you a young man who's working with the staircase where we removed every other rod, and he's asked to explain what the successor function does.
What have you done? Are you doing suck or what was the other one? Creep.
I'm doing suck.
Okay, and what does that mean? What does that mean you do?
It means like if I do suck, you add one number on. Like if I had 6 and I done suck, it will equal 7.
Okay, all right. And then but you do it as
It's actual 8 because there's no odd.
So if we try and model what was that child doing, he clearly had an idea of rods modeled as instances of the Haskell type color, trains as expressions built from sum C, and patterns as equations with equivalence. So he's working in this complements domain, and I call this the conceptual model at that point in time. If we measure the rods with some unit, we can map the rods and trains to ints. So here, sum C, if it has its 2 arguments, it maps to a color, which is the sum. A measure function, a measure functor will take these 2 colors and map them to 2 ints, and it will map the sum function to the plus function. Here they are spelled out in Haskell. And again, I'm using the fact that suck and pred are polymorphic functions, so they read across naturally. And in fact, the children have no difficulty with the interpreter understanding that the successor function can be applied both to a color and to an integer. If we go back and look at Quintanillo's key cycle that I drew attention to before, what we can see is the conceptual model is providing a way of articulating the imagery. We've got a mathematical model in symbols for the arithmetic. We've got the domain-specific language, which is a very simple language in this case, a specification model, which is the type signature, and an implementational model, which is the equations, the defining equations. Now, I said I'd briefly touch on an exercise for co-design with teachers, which typically we would engage them 1 day per half term on this kind of work. They'd be reporting what was happening in the classroom, and we'd be working on the next set of lesson designs and lesson plans. But here I'm taking the pattern, which I call Ferrer table, after Norman Ferrers, who invented a way of representing integer partitions. This number in Ferrer's notation would be a 6 plus 5 plus 4 plus 4 plus 3 and so on. The first column is a Ferrer diagram. If you look at the conceptual model looking for patterns of recursion, you might see that built within this, within this pattern here is the Ferrer table for the rod that is 1 less than it. And then there are some others which don't have a white in. What I'm going to do is develop an implementation of some code of an algorithm that will generate this picture. So we start by organizing the trains into equivalence classes according to the number of rods in the trains. and we give them this is the equivalence class P sub 2, with the 2-car trains equivalent to a D, 3-car trains equivalent to a D, 4-car trains equivalent to a D. And we choose a representation of the list of ints for those partitions. So partitioned into what with 1 car is a list of 6 in it, and so on. The first step in the recursion is to identify that mathematically, if we use k for the number of cars and n for the general length, pkn is going to include within it the number of 1 less car trains in a 1 less rod. You see what I mean? Is that clear? We can model that process of adding the whites by functor map, an F map, which appends a white one, a 1, at the end of the representation of the yellow pattern. The second step is to recognize for the remaining trains that if you take a white away, the difference between the white and these 2 cars here, so you get these 2, you've got 2-car trains and 2-car trains, but this is n minus k. You've taken k whites away. In this case, it's just 2 of them. And if we go this way, we're mapping 1 there and 1 there. So the specification model is both in mathematics and in Haskell, 2 distinct representations of the pattern. And the implementation model in Haskell drops out from the specification by taking those 2 equations and adding them and appending them. That's the integer partitions of k cars, and summing them all, which I haven't done here, will take you to the full conceptual model. So we can adapt the earlier diagram. We've explored how to build the integer partition from the integer partitions, and we can see there's an equivalence between the conceptual model and the implementation model. And that code can be distributed via REPL. It's used with year 8 classes now to all the children, and they can begin, or in our case, to the teachers, and they can begin to work and interrogate the code themselves through the web. So in conclusion, I've offered you a categorical model of algebraic reasoning. Sum C corresponds to plus, Ferror table corresponds to the integer partition. We are engaged at the cutting edge of maths and informatics. Our thanks go to all the people who've helped along the way, including funding it. And thank you, Philip and Omar, for inviting me today.
You violated a tradition. You finished early rather than running over.
That was because I'd hoped to have some questions from the audience, either here or out there. I have prepared some extra slides, of course, if that's necessary, but hopefully that won't be necessary.
So, any questions from the room?
Yeah.
So the algorithm which you showed, which was named for teacher, was that introduced to the kids at all?
The algorithm for the teacher doesn't go to the children. I want to make it clear here that what happens in the classroom, the teachers lead. My job and the job of the researchers is to observe what's happening, comment on it, and suggest exercises by breaking these problems down into subordinate problems, which are ultimately tractable for the teacher to put in front of the children. That could mean that a whole lesson would be devoted to a single equation. plus minus 1, say, of a pair, where you were with the table of confidence, you saw one of the arguments was increasing by 1, one was decreasing by 1. That function could be a whole lesson. But what the teachers found valuable was the interaction as peers with us as mathematicians. Because the subject, what they see of this is a deficiency in their subject knowledge. And once they get into it, they see the deficiency in their pedagogy. But it's a continuous dialogue that you have to have in the classrooms. And the scaling up of the project I've been talking to Philip about is to try and remove the mathematician from the delivery, the mathematician researcher, so that the teachers can do more self-help. And I see the programming environment as being a very important part of that.
You're hoping for some sponsorship for a research project. So what you said has been really interesting. What's been done so far, and then what's the research project adding to that?
Okay, so what's been done so far at Stanford is to track the children's algebraic reasoning and arithmetic fluency with an instrument that measures their performance every term in the second year. We're not looking for how their performance improves through programming. It was a very small part of that project, the programming exercises, with 280 hours of continuing maths and 10 hours of computing. Mm-hmm. What we now want to do is to elaborate the assessment instrument so that we can assess the coding proficiency of the teachers and the children and correlate that with their mathematical performance in year 3. Because we believe that having given them this trampoline to jump from, they will excel in mathematics because of their exposure to computing. And we have to
do some measurements that show.
We're going to develop a measurement instrument. The project we're proposing will, as a research project, develop an appropriate instrument with colleagues at Stanford who are statistical analysts, really experimental educational psychologists. We're looking for help in building the user interface and the functionality of the assessment instrument specifically.
So roughly what you're hoping to show, if I've understood this right, is you can teach students maths using this approach. Mm-hmm. Or you can teach students maths and computing using this approach.
Yes.
And you want to show that teaching maths and computing, they learn more, it's more effective.
Yes.
Than just
That's
teaching
right.
maths.
That's correct. Yeah, you put it better than I did. Yeah. Yeah.
So I have some questions about how the computing tool, the DSL work. Do the students are actually typing things into these?
Yes, yes, yes.
Or not accidentally, sort of invokes some other Haskell function.
Yeah.
Anyway, it's really weird. There are messages.
Yes. Yeah, I think you're asking about the brittle nature of a programming environment if you move beyond the constrained domain language that you want the children to be constrained with. And you're quite right. I think learning to live with brittleness and recover from it is one of the important skills that the teachers particularly will need to have. And part of this is to create an environment for the teachers training, which is like the environment that the children they're teaching are going to find when they get out into the workplace. So we're upskilling the teachers first. The tool that ultimately gets in front of the children, yes, it has to be carefully engineered and locked down for safety reasons. And we've done that with the tool we're using. The Stanford Educational Assessment is a very robust set of protocols. Yes, exactly. And the feedback you get from Haskell with syntax errors or alignment errors, you're not with the right number of spaces or whatever, can be very, very opaque. But children can learn very, very quickly. First of all, they like breaking things, and then they learn how to recover from it, and they help each other. I mean, the noise in the classroom when they're programming is absolutely off. There's a lot of noise when they're playing with the rods because they have a free play with the rods every session, and that's the rods banging around. But when they're programming, they're talking to each other about what they're finding. and some of them find things earlier than others find things. I think what we found was that things would break, but they break in a systematic way. So after a while, those circumstances are recovered from. The other thing we noticed by putting examples of the children's work up on the whiteboard, like behind me here, they could critique syntax errors themselves. The spot the difference puzzles are in all the kids' magazines. So they're used to looking and finding very fine distinctions, perhaps more than adults would be.
Yeah, I have to say that we've described the students in the class as responding to syntax errors. It sounds like your primary school children are far more robust than our first-year students.
Yes, I think there's a lot to be said for that. Yes.
Something that the study might look at, which is how does this technique work when you have more neurally diverse children? Do they do well with it? They tend to do less well with it. It's not clear. That'd be interesting to study.
Yeah. Yeah.
Good idea.
So we have a question from the remote listener.
Good.
Martin Island, do you please unmute?
Hi. Ian, I got a question which it's quite difficult for me to articulate clearly. There's a kind of big difference at some level between the rods themselves and Haskell. I mean, the rods are physical things, visible with colors and all sorts of stuff. And Haskell is, well, something that you doubtless can type into something or other, but has a kind of abstract structure. And in this, in some sense, you're marrying the two, right? Now, one thing that I think is an issue with maths education from very early on is the fact that, as it were, children are different, right? Some people find certain kind of styles of thinking easy and other styles not, and vice versa. So is there any possibility of using, as it were, this project in some sense to negotiate round that, so that, you know, it's possible to advise teachers that if they have when they have a child that's having fun with the rods but kind of hates the Haskell, they react one kind of way, and equally a child might not really like the rods but really get off on the Haskell, and then it's another kind of issue. So I suppose I'm suggesting that there's a potential, because of that difference between them, for something quite creative if you think of it in terms of actually, you know, not everybody is going ideally to love both parts of this. What do you think?
Martin, yes, I think there is a theory about learning styles which emphasizes the distinction between learning abstractly and learning through concrete operations. What Gitenio is attempting to do is to put them into a coherent orchestra. And that doesn't mean that some areas of activity won't be weaker than other areas of activity at some point in the child's learning journey. But I think he would argue that it's the way they all interact which is the value, rather than rote learning of facts or some other preferred way of teaching. I think that the way in which our brains are excited when we think mathematically suggests there are many different areas involved and engaged in that. And it's the connections between those areas, which are either stronger or weaker, that determines how effective people are working mathematically. So yes, I think a subtle understanding of that model can help diagnose, it can help formative assessment, it can help teachers decide what next to assign to the children. And I think it's a continuing conversation. It's never going to end. This learning in the classroom is not going to stop.
No, I mean, I accept that. I guess I'm just thinking that at the edges, there will be children for whom one or other component of this thing is really substantially less agreeable. I mean, you see that at university maths. There will occasionally be somebody who comes to Cambridge and they simply cannot cope with the abstract idea of a vector, whereas they can handle matrices and whatnots. You know, they're absolutely fine with that, right? And I mean, I think stuff like that happens really, really early. I mean, I just add another thought, which is the question of assessing the effectiveness of things like this. I think one of the difficulties with it is that, I mean, if it goes well for a child, a lot of the benefit will not be seen until very much later.
Yeah.
I mean, so there are kind of questions of, can you follow a collection? I mean, I don't think one should be really looking for the children to have, you know, to have done well in the next couple of years, so to speak. I'm inclined to think that, there are places where they're going to be confused about, where children are typically terribly, terribly confused. You know, so I don't know whether, you know, it used to be the case, I'm not sure now, that you were told to teach fractions at the end of primary school.
Yes, that is.
And it's kind of, you know, the confusion is absolutely riotous.
Yes.
And it would be more interesting in some sense to see whether children who'd had these early experiences, almost immaterial of how they were taught after that, whether enough is still there, that they at least have a feeling for what a third of 3 is.
Yeah.
When they go into that. So I would be looking for it much later.
Yeah, yeah. I would hope that in partnership with people in government that are responsible for the efficacy of the school system as a whole, that we can carry out that kind of longitudinal research.
Well, I hope so too, Ian, but you know, I'm not that optimistic about government at the moment, because I had a lot of dealings with Nick Gibb, Minister of State for Schools, and his picture of what a school should look like is exactly not like the things that you were showing us.
Yes.
He wants the kids out there in a line, busily doing sums, right?
Yes, yes.
They're not going to learn anything that way.
Yes.
So good luck with that.
Yes. What is tragic, what is really tragic about the school system is that teachers know that's not working. And nevertheless, their professional discretion has been so circumscribed that if they try and do anything different, they're out on a limb professionally and career-wise.
I'm absolutely with you on that.
But I'm not hopeless about this. I went to ask Madeleine Goutard. She was in her 80s when I saw her. She was Gatenio's close collaborator. You recall, that produced the Louis, the French-Canadian child's work I showed. I asked her why had this been forgotten, and she said she didn't have an answer to that question, but she wasn't worried about it, because if humanity has invented something, it'll invent it again. And in a way, that's what we're doing.
Yeah,
we're reinventing it. So
thanks.
I've used all our time. Thank you, Martin, for that question.
Sorry.
Do you have any ideas for using similar methodology later on?
Yes, in fact, this is part of a bigger project, which is a pro bono project by the Maths Teachers Association, where I work as convener of the work group on functional programming and computer algebra. I mean, basically, we want to tackle the full school curriculum. I'm concentrating on Key Stage 1, which is the beginning of year 3 now, from my professional work. Other colleagues are working at other levels and in other departments. to try and move the thing along in parallel, basically. So if you're interested, if anybody's interested in coming to ATM's conference, you'll see 70 odd presentations, of which maybe a dozen or more are inspired by this movement to bring computer science and mathematics together. It's a very exciting place to be.
So one of the questions here is how it's going to, if you succeed, how you would scale it. Like this only works if you have teachers who are trained.
Yeah.
Maybe the teachers training can be difficult. Have you thought at all about how this might scale?
Yes, yes. And as I said, we can't really, we haven't got time to talk about the detail of that now, but I'm happy to talk to you about it over dinner.
We could continue.
Yeah.
So let's then hear again. Stop the